Welcome back to Dissect the Question. A man is reporting to his primary care physician that he is being awakened from sound sleep several times a week by sudden onset of muscle spasms. Physical examination is unremarkable. Which of the following physiological mechanisms is most likely to be responsible for muscle spasms? Well, there's not much to dissect in the clinical vignette. It's referring to spasms, and it seems like it's skeletal muscle spasms. And here we have in the lead-in, spasms again. So our mind should immediately go to what is a muscle spasm. A muscle spasm, you will recall, is a contraction without relaxation. That's why it's so painful, because when we get contraction without relaxation, pain receptors can be stimulated. And pain receptors then, being stimulated, cause us to stop what we're doing. And maybe when we stop what we're doing, the muscle will relax. So that's the logic behind a muscle spasm. The next question you would ask is muscle spasm a high excitability state or a low excitability state? It's high excitability, isn't it? When we have contraction without relaxation, we have too much excitation, don't we? That seems logical too. So let's see if we can notice in A, B, C, D, E options something that's going to jump out at us as increasing excitability of either the motor neuron that's responsible for releasing acetylcholine, depolarizing the skeletal muscle, or depolarizing the skeletal muscle in the absence of the motor neuron. Let's see how that would work. The motor end plate is represented in A, and what a motor end plate is certainly just the area where we have a motor neuron releasing the acetylcholine from vesicles at its terminal onto skeletal myocytes with acetylcholine receptors, ACHRs, and we know part of the ACHR unit is the acetylcholine esterase, which breaks down the acetylcholine to protect against overstimulation. Now, if the motor end plate, which is right here, here's the motor nerve, and the end plate, this whole area is called the motor end plate. We also call it the neuromuscular junction, but the motor end plate is a certain part of the neuromuscular junction where all this happens. So if the motor end plate becomes less permeable to potassium, what's going to happen? Well, we have to know what's the role of potassium here. We said there's an acetylcholine receptor with acetylcholine esterase, but part of that acetylcholine receptor is a channel called a non-selective cation channel, and it's non-selective for sodium and potassium. It's a very unusual channel because usually in the nervous system, if we say non-selective cation channel, it's non-selective for sodium, potassium, and calcium. But in this case, it's only sodium and potassium. So when acetylcholine binds to the acetylcholine receptor, it opens this channel and allows sodium to enter and potassium to leave. Here's sodium entering, and here's potassium leaving. Because sodium rushes in under a much higher electrochemical gradient, very quickly, more sodium enters than potassium leaves in the beginning, and that's why we get the depolarization that leads to contraction of the muscle. Now the potassium leaving, because we have a plus coming in and a plus going out, the plus going out with potassium is kind of lessening the effect of sodium, isn't it? But if we decrease the permeability to potassium, which way is potassium moving out? Potassium will accumulate here inside, making the inside more positive, and that's not supposed to happen. If that does happen, would that create more excitability? Yes. So A jumps out as the best answer. But we don't know. We know it's only an answer. It seems like a very good one. But in multiple choice questions, there are often two correct answers, and it's incumbent upon us, and we're required for examination purposes to always select the best one. So let's see if we can eliminate the other four so that A for sure becomes the best option. Decreasing permeability of motor end plates to sodium. So if less sodium comes in, we're going to have less excitability. That's not muscle spasm. Muscle spasm is more excitability. So let's get rid of B. Decreasing permeability of motor neurons to calcium. Well, here's the motor neuron. And when calcium comes in through a voltage-gated calcium channel, it's responsible for exocytosis of the acetylcholine. So if we decrease permeability of the motor neurons to calcium, then we're going to have less release of acetylcholine by exocytosis and less excitation of the muscle. This is not going to be responsible for muscle spasms. Something like this would inhibit the muscle spasms by decreasing excitability. So we're going to get rid of that one too. Let's look at D. Decreasing permeability of sensory neurons to sodium. Well, where do sensory neurons come into this story? The only sensory neurons we have embedded in a muscle are associated with the muscle spindle. The muscle spindle. Muscle spindle. Embedded in the belly of the skeletal muscle to sense the tension and control muscle tone. Remember? Muscle spindle controls muscle tone for the stretch reflex, or what we call the myotatic reflex. When we use a hammer to tap the tendons, it stretches the muscle spindle and we get a contraction of the muscle that has been tapped, or the muscle associated with the tendon that has been tapped. And we call that the deep tendon reflex. And that's how we evaluate the nervous system, by tapping tendons and looking whether the reflex is appropriate. It's a measure of muscle tone. So, if we decrease permeability of sensory neurons to sodium, the sensory neurons in the muscle spindle are going to become less active, and the muscle tone will decrease. If the muscle decrease, that's not a high excitability state. That would inhibit the muscle spasms, wouldn't it? So it seems like we can get rid of D. And now what happens if we increase permeability of motor neurons to chloride ions? So here's a motor neuron, and we're going to take chloride, which is an anion a negatively charged ion, and we're going to bring it inside. Well, what we know about excitable tissues is when the inside becomes more negative, we are repolarizing or hyperpolarizing, aren't we? That would result in repolarization or hyperpolarization, which is not creating more excitation. More excitation would come from sodium entering, a positive ion entering. When a negative ion comes in from the extracellular fluid to a motor neuron, it decreases excitability. So again, the motor end plate is going to become less excitable by increasing the permeability to chloride ions. So it seems like we're very sure that A is the most appropriate and best option here.